Can you guys hear me? Hello. Hello everyone. So can someone reply in the chat? Okay. So today we're gonna discuss uh, questions from week 3 lectures. So these questions will be helpful to solve assignment problems given in week 3. And I think in this topic in these lectures several topics were covered from metric space mainly, so such as like complex sets, sequentially complex sets, Henny-Borel theorems, Cantor sets, limit points, and I think the definition of sequences and some of their properties, right? So what I'm gonna do is uh, I'll start solving some questions, and whenever it is required uh, I'll be explaining those theories. Okay, is that fine with everyone? So I'm not gonna explain theories in the beginning, so whenever it is required for each questions I'll be explaining accordingly. Okay, so we'll start with first question. Okay, so consider consider the sequence an where an is n square plus 1 divided by n square. Okay, then which of the followings are true? Okay, so the first option is an is a oscillatory sequence second option is an is a convergent sequence okay. N is convergent. Third option is N is divergent. Okay, and last option is none of the following above. Okay, so I'm starting with easy questions, and then we'll go to the hard questions. Okay, so do anyone know this answer? Is the question clear to everyone? Yeah, what is the answer? So if you don't want to speak, you can just type on the chat. So this is like an interactive session. Okay, this is like you can ask questions to. Sorry, Nagraj.
Yes, sir. It is a convergent.
Okay, but why is that?
From my side, taking the n square common,
Okay,
then cancel out the denominator.
okay,
Then limit is tending n is tending to infinity. Then we get the first part is 1. Next term is infinity.
next time is what?
1 by infinity is I think 0. I don't know about that. I think I guess it.
Okay,
We get 1 is the answer for it is not.
okay, yeah, this is true, obviously. Yeah, I mean, like it's like 1 by n square goes to 0 as n goes to infinity. So can you prove that y n square 1 by n square goes to 0?
I don't know, sir, about that.
Okay, I see. So actually, this sequence is very simple. So you write an as 1 plus 1 by n square, and this is same as n square plus 1 by n square, right? So you just divide it by the denominator, correct? And this will imply that limit an is limit of 1 plus 1 by n square, which is 1, because limit of 1 by n square is 0. But I encourage everyone to prove that limit of 1 by n square is 0. Okay, so you go through by definition of a sequence, the convergence of a sequence, and then you try to prove that that limit of 1 by n square is 0. Okay, so this is an exercise. So clearly,
Sir, you can prove that for how it is 1 by n square, it is infinity. I don't know about that.
sorry, I didn't get you what you were saying. Your voice is breaking.
Hello?
Yeah, tell
Now
me.
it is audible, sir?
Yes, 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 yes.
1 by n square is actual infinity, na? 1 by infinity is 0.
Okay.
What is the proof for that? How can it is say it is 0?
That's why I'm telling, no, you go through the definition of a sequence, then you will get. So what is the definition of a convergent of a sequence? I mean, when you say a sequence xn converges to some x.
That is limit extending to n extending to infinity. It's not.
No, no, not the limit definition. I'm asking the definition, like the epsilon definition. Do you know any epsilon definition?
Forget that, sir.
Oh, okay. So a sequence xn converges to x if given epsilon greater than 0. So let me write it here. So a sequence xn, let's say I'm working in a metric space. So here it is converges to 0, or let's say converges to some x uh, if for any epsilon greater than 0 there exists a natural number let's say n0 in n, such that there's a distance between xn and x is less than epsilon for all n greater equals to n0. Okay, so here x comma d is the metric space. So this is the definition of convergence of a sequence in a metric space. So that means that after some natural number, the distance between xn and x will be always less than epsilon, or in other words, you can always contain all the term of the sequence in a ball of radius epsilon. Okay, so ball means here an open ball. So this is the definition of a sequence which converges to some number x. So now, since I have asked you to prove 1 by n square converges to 0, so that means you're gonna work in the usual metric, right? The space is R and D is the modulus function, I mean the modulus distance, right? So then you just, like, the D will be replaced by modulus of xn minus x, correct? So instead of xn, you just put 1 by n square, and since we are claiming that it converges to 0, you replace x by 0. Okay, so that means 1 by n square will be less than epsilon, and then you have to find out when or what is the natural number n0 such that this is happening. So I'm showing it once, and I'm not gonna show afterwards. Okay, so for this sequence 1 by n square, this converges to 0. Okay, so we are working in the usual metric. So usual metric is the modulus function. Okay, and we have to show that 1 by n square minus 0 is less than epsilon, correct? So now our task is, since epsilon is arbitrary, we have to find out a natural number which depends on epsilon. Okay, so this will imply that n square is less than, greater than 1 by epsilon. Okay, and this will imply n greater than 1 by square root of epsilon. Okay, so now how to choose the natural number n0? Can anyone tell me how to choose the natural number n0 such that for any epsilon greater than 0, 1 by n square minus 0 will be less than epsilon? Anyone? Nagaraja, do you know? Because I have shown 90%.
No, sir.
Yeah, do you know? I didn't understand what you say.
No, sir, I don't know.
Oh, okay. So what you do is, you see, you are almost done, right? So you have to just find out that n0. Now you need n greater equals to n0. Now see, 1 by square root of epsilon need not be a natural number, right? So what you're going to do is, you're going to take the box function. So you just take the natural number to be 1 by box function of square root of epsilon plus 1. Now if you take like this, then your n0 will be an integer, and then if you take n greater equals to n0, which will be always strictly greater than 1 by square root of epsilon, correct? So this will imply always 1 by square root of epsilon. And now if you are wondering why this happens, so you can follow the last class, the week 2 class, where I have explained what is a box function, what are the properties, and how this inequality comes. Okay, so from here you can see that our candidate n0, which depends on epsilon, is box function 1 by square root of epsilon plus 1. Okay, so that means given epsilon greater than 0, you can tell that this is the sequence n0. I mean, this is the natural number n0 for which this sequence converges to 0. So I hope this is clear to everyone. Is there any doubt? Is everyone getting it? So if you don't want to speak, you can just reply in the chat so that I will understand that you are also following up with me. Okay. Please always put thumbs up or yes or something in the chat. Okay. Everyone. So now we'll go to the next question, which is question number 2. So let the sequence an defined by an equals to minus 1 to the power n minus 1 divided by n factorial, where n is a set of natural numbers. Then which of the following is true? So I'll encourage everyone to solve with me. So you also write with me so that you can understand every words or every questions instead of just listening to the video. Okay? Because this is an interactive session. This is a one-time opportunity for you. If you have any questions, you can ask me. Because in the next class, you will not be able to ask me question from week 3, right? So if you have any doubts regarding the topics that has been covered in this week, you are always welcome to ask me any questions. Okay. So the first option is sorry. An has one limit point. Second question is, second option is an has more than one limit point. Third option is an has no limit point. Fourth option is an is not bounded. Okay. Is this question clear to everyone? Any doubt? So which option is correct? So how this sequence looks like? Nagaraja, do you have any opinion? Okay, anyone? There are 6-7 guys here, right? Can you guys hear me? You can just answer in the chat if you don't want to speak. Okay, I assume you all are getting it. So the sequence, you can see that it is multiplied by, I mean the 1 by n factorial is multiplied by minus 1 to the power n minus 1, right? So if you vary n, for example, if you put n equals to 1, you get 1 by 1 factorial, right? Because minus 1 to the power 0 is uh, minus 1 to the power 0 is 1, correct? So that means the sequence will look like this. So it will be minus 1 to the power 2n minus 1 for n even, and divided by 2n, oops, sorry, correct? Just 2n minus 2 factorial when n is odd, correct? Now can you guys get it what I am doing? Correct. So does it make any difference here? Anyone, guys? Oh, yeah. So it will be 2n, right? Because it was yes, it was in fact n factorial, so it will be 2n factorial. Yeah, this is correct. Yeah. Yeah, I thought it is n minus 1, so that's why. Yeah, so it will be 2n factorial and 2n minus 1 factorial. But you see that at n, like as n goes to infinity, both goes to 0, right? It doesn't matter if n is even or odd, correct? So n will go to 0. But suppose if uh, is my screen available to everyone? Can you guys all see my screen? Nagaraja is complaining that he cannot see. So probably it is your internet issue. So mine side is okay. Okay, so now if n was given like this, then only it will cause a problem. Okay, because then it will be minus 1 when n is odd or 1 when n is even, and that in that case it will not converge, right? But in the previous case I can see, or we can see, that limit a n is 0, correct? So if a sequence is converging to a point, then the limit point will be always unique, because every subsequence will also converge to the same limit, correct? So for this particular question, n has one limit point, correct? Is that clear to everyone? This is easy, right? Okay, So now let us go to the next question. Question number 3. So consider the uh, set of rational numbers q, okay, and e equals to 1 by n square, such that n are natural numbers union 0. Then which of the following is true? So first option is both q and e are compact. Second option is q is compact but e is not. Third option is q is not compact but e is compact, okay. And fourth option is none of the following above. So this is a good question, because from here I'm gonna ask like a lot of questions. So can anyone tell me which option is correct? So if you don't want to speak, as I have already said, you just can reply on the chat, okay. You can just type your reply in the chat. I mean, then I'll understand, like, your guys following up with me. So yeah, so there are two sets are given, and the question is about which of the following are compact. So first of all, what is the definition of a compact set? So let's say what are the compact sets in R. Because Henry-Borel theorem was taught in week 3, right? In week 3 lectures, Henry-Borel theorem was taught. So probably you guys know what are the compact sets or the definitions of compact sets in finite dimensional spaces. I mean finite dimensional Euclidean spaces, right? So what is the definition of a compact set, or what are the characterizations of compact sets in R? Subrat, Dibyalochon, do you guys know? Closed and bounded. Okay, yeah, that is true. That is by Henry-Borel theorem, right? Is that correct? Yeah. So let me state the Henry-Borel theorem first. Okay. So so it says that a subset K of Rn is compact if and only if K is closed and bounded. Okay. Okay. So this is called Henny-Wall theorem. So if the space is finite dimensional, or if it is a finite dimensional Euclidean space, then compact sets are just closed and bounded sets. Okay. So since here n equals to 1, that means set of all real numbers is a one-dimensional space, right? It's just on a straight line. So the compact sets will be just closed and bounded sets. So we have to just verify that which of the following sets or which of the given sets are closed and bounded. Okay. So let me start one by one. So the first set is Q. So now can anyone tell me, is Q closed? Is Q closed? Yeah, so could you tell me why Q is not closed?
The limit points will not be there, the irrational numbers.
Okay, so how do you know that the limit points of Q are irrational numbers?
It can be rational and irrational, but the irrational won't be there, no, in the set.
Yeah, that's okay. I'm asking that why, like how limit points of Q are irrational numbers. I understand that in Q there are no irrationals, but why is that true? Like why you are claiming that?
I don't know that.
Okay, so I mean in the last class I think I have discussed this, but I didn't give the example, the why Q is not closed, and the similar example is why Q is dense in R. Okay, if you can prove why Q is dense in R, then you can easily prove that why Q is not closed. Actually, the Q closure is whole of R. That's why Q is not closed. Okay, so a set is closed if and only if it contains all of its limit point, right? So that means if K is a closed set, the set of all limit point of K, which is also called derived set, that also has been covered in this week lectures. So if K is closed, K prime should be subset of K. So it should contain all of its limit point, right? But Q has not only rational limit points, but it has irrational limit points. Now, how does that follow? Like, why should I say that? I'm saying it because Q is dense in R. Now, dense in R means if you choose a real number, let's say A, you can find a sequence in Q such that that sequence will converge to the real number. Okay. Now, real number contains irrational number as well. So that means if you choose an irrational number, you can find a rational sequence which will converge to that irrational number. But that irrational number is now not belonging to Q, right? So now I'm gonna prove that. Okay, I'll give a like super important counter example. I mean super important example. Please remember for the rest of your life this example, and it is very helpful to prove why Q is dense in R and why Q is not closed. Okay, so let's say alpha is in alpha is an irrational number. Okay, so that means this is in R minus Q. Now I have to find a sequence xn from the set of rational numbers such that xn converges to alpha? Do anyone know? Because the other part is easy. If you want to show that for every rational number there is an irrational sequence, this is easy, right? Because if alpha is a rational number, you just take alpha plus square root of 2 divided by n. Then that will be an irrational sequence and that will always converge to alpha. Correct? But what about the converse? Given an irrational number, how to find a rational sequence? So if you guys have followed the last class, then you might have noticed that I had discussed box function. And using box function, I'm gonna construct this sequence. Okay, so define the sequence. Box function n alpha by n. Okay, now in the last class I've already explained that box function is a function from R to Z. Correct? So that means xn is always a rational number for each n. Correct? Up to that, is it clear to everyone? So then only I'll go ahead with the convergence part. What about other people? Binu, Hema, Subrat, Tibyalochan. Are you guys getting it? Because I'm not getting any answer. You can just put thumbs up, or just yes in the chat. Because, yeah, it's for you only, right? So, okay. Now I'll show that xn converges to alpha. Okay. So, in the last class, I have also proved that for any box function, this thing holds. Okay. So for any box function x, box function of x will be always greater equals to box x, because box x is the leftmost integer function, right? That's why it's called the greatest integer function. So you take the leftmost integer of x. So for example, if x is 1.5, the box x will be the left integer of 1.5, that is the closest left closest integer, which will be just 1. Similarly, if you take like box function of minus of 2.5, then it will be minus of 3. Okay, so this inequality always holds, just remember it. Okay, and also I have proved this inequality in the last class, so you can follow the last class as well. So from here you can see then that box function of n alpha less equals to n alpha less equals to box function of n alpha plus 1. Okay, is this clear? So then 0 less equals to n alpha minus box function of n alpha less equals to 1, right? So what do you need now? You need box function n alpha divided by n. So you multiply both sides, divide both sides by n. So it will be 0 less equals to n alpha minus box function of n alpha divided by n less equals to 1 by n. So this is actually a strict inequality. If you want, you can just write strict. Okay, this can n alpha can never be box function n alpha plus 1. So box function n alpha plus 1 will be strictly greater than n alpha, and if you just write less equals to, that is also fine. Okay, that is not a problem. So this will imply 0 less equals to alpha minus xn. strictly less than 1 by n for all n, right? Now do anyone know what to do after that? This is the master step, a famous lemma or famous theorem. Do you guys know that? What should we apply to this inequality such that limit xn is alpha? Anyone? Nagraja, do you know? I'm just asking. Okay, if you don't know, that is also okay. Like, this is just an interactive session, so that's why I'm just asking you. Like, if you guys know, that's okay. If you guys don't know, that is also fine. Okay.
Don't know, sir.
Okay. Sure. Yeah. Any other guys? Any other? Philo. So there's a.
If we tend n to infinity,
Okay. Tell me.
if we tend n to infinity,
But okay, then what are you applying? Like, if we apply. Yes.
Sandwich theorem we can apply. Sandwich theorem.
Yes. So do you know what is the alternative name of sandwich theorem? Like, just asking. One name is always okay. Okay. So what you can do is you can just apply sandwich theorem both side. Okay. So sometimes sandwich theorem is also called a mousetrap principle, because you see that alpha minus xn is trapped from both sides, correct? So that's why sometimes it's called mousetrap principle, and so this is implying that limit xn is alpha. Okay. So for those people who do not know what is sandwich theorem, I just write the statement. Okay, so you guys try to prove how this follows. So now I hope this is clear, that we have shown for each irrational number there is a sequence of rational numbers that converges to alpha. So in the last class I had given a hint that it should be constructed using, or one of the options is to construct using the box function, because box function has the ability to to change the real numbers to a integer, right? So then that means you can construct a rational number, right? So that's how we have constructed the rational sequence xn, such that given any irrational number, it is converging to that irrational number, and obviously xn is in q for each n. So I hope this is clear to everyone. And sandwich theorem, so I'll just write it here. So let an, bn and cn be three sequences such that and an less equals to bn less equals to cn for some n greater equals to n0. Okay, so it need not be necessarily hold for each n. If there exists an n0 such that it holds after that fixed natural number n0, then this is also fine. Okay, so then limit bn is also a. Okay, so yeah, I hope this is clear to everyone. This is called sandwich theorem. So you can follow that book I suggested in the last class, that is the book called Schema Real Analysis. So here I think that this theorem is there, and probably they have also proved. Okay, so yeah, so if this question is clear, then I'll I'll solve why Q is not closed. So I think now it is clear why Q is not closed, right? So I forgot in the sequel what was the question. So yeah, I hope it is clear, right, why Q is not closed, because given an irrational number you can find a sequence from the rational number set such that it converges to the irrational, but irrational does not belongs to Q, so Q is not closed. So we have answered two questions: Q is not closed and Q is dense. Okay, so what about E? Is E closed? So is this set closed? The set E? This is a closed set, right? Because it has only one limit point, and that is belonging to the set itself, right? Yeah, so that means E is closed. And since Q is not closed, not bounded, Q is not compact by Henry-Borel theorem, because both are subset of R. But since E has only one limit point, right, that is 0. The set E has only one limit point, which is 0, and 0 belongs to E. So E is closed. Also x is less equals to 1, correct, for each x in E. So this implies that E is bounded, correct. So every element of E is less equals to 1, so that means E is a bounded set also. So E is closed and bounded, is a subset of the finite dimensional space R, so that means E is compact, correct. So is it clear to everyone? Okay.
Yes.
Okay, so other are following up, I assume. So that means Q is not compact, but E is compact. Okay, so then we'll go to the next question.
Sir, since Q is not bounded, we could have directly concluded that it is not compact, right? We didn't have to prove the closed property.
Yeah, that is true, but I just wanted to show why Q is not closed.
Yes.
Because in the last class I said that I will give a sequence from rational number that will converge to given an irrational number. So that's why first I showed that why Q is not closed. Yeah, of course Q is not bounded. Why Q is not bounded? You tell me.
It goes till infinity.
What goes to infinity?
Sequence of Q.
What sequence of Q goes to infinity? Tell me. So a set is bounded means it can be contained in a open ball, right?
Yes.
But Q cannot be contained in open ball, right? You can just take the sequence of natural number.
Okay.
Correct. So yeah, because every questions comes down to the fundamental definition in mathematics. So if you try to prove boundedness, you can just use, I mean, you can obviously say Q is not bounded. That is of course true, but to prove it fundamentally, you can just use like the definition of boundedness. Okay. by taking a sequence of natural numbers. So that is also fine. So here I showed, because in the last class I promised that I will show Q's tens in R. So it answers both questions, that Q is not closed and Q's tens in R. Okay. So now I'll go to the next question. So this should be question number 4. So this is the question from metric space. So let x comma d is a metric space where x is R and d is a discrete metric. Okay, so I hope everyone knows what is a discrete metric. I mean, how the distance is defined, and if you don't know, then I'm just defining it here. So d of xy is 0 if x equals to y, 1 if x is not equals to y. Okay. So then the sequence 1 by n is, so the first option is a convergent sequence. Second option is not convergent, or let's say divergent. Third option is none of the following above. Okay. This is a very important metric space. I mean, a lot of questions has been asked in competitive exam, such as NET or GATE or whatever you exist in mathematics in India actually. So the first task or the first exercise will be to prove that this d of xy is a metric. Okay, so I think in the last class I had given the definition of a metric space. So now your job is to prove why d is a metric. So not right now, you can do it in your free time. So first try to prove that this is a metric. Okay, so now let's come to the question. So this is a very interesting question. So I'll not just only solve this question, I'll be solving for any sequence xn. Okay, so like if I give you a sequence xn in a metric space, in a discrete metric space, then how you can characterize the convergence of the sequence. Okay, so if you can characterize the sequence, I mean the convergence for any sequence xn, then you can do it for 1 by n as well, right? So do anyone know what is the answer? Anyone?
Convergent.
Are you sure?
It's not convergent.
Yeah.
Discrete metric.
Why is it so?
Distance, so if we suppose the assume that sequence is convergent to some alpha,
Okay, then
by definition of the convergence, if we take any epsilon greater than 0, the distance should be less than epsilon. But if you take any two elements in that sequence, the distance should be equal to 1.
okay, then
Either the distance is 0 or 1. So if epsilon is suppose half,
yes.
and distance will become 1 less than half.
Which is a contradiction.
Yeah.
So now you tell me then, what are the convergence sequence in a discrete metric space? Can you give me an example of a convergent sequence, or the set of all examples of convergent sequence?
Constant sequence, constant.
What else? constant sequence is very trivial, right? It converges almost everywhere. I mean, in every metric space. What about non-trivial examples? Okay, so yeah, uh, I'll start with an arbitrary sequence xn, and then we'll try to see if xn converges to x, then what happens to x. I mean, what happens to xn. Okay, so yeah, let's solve this question. Okay, so so let xn in x such that limit xn is x for some x in x. Okay, so here x is the discrete metric. So let's say the limit is converging to x for some x in x. So now we'll try to see what x looks like and how to characterize this sequence, right? So now you see that d of xn comma x, this will be 0 if xn equals to x, and this will be 1 if xn not equals to x. Correct? This is the definition of discrete metric, right? So now if we say that xn converges to x, so that means given epsilon greater than 0, there exists a natural number such that d of x and x is less than epsilon for all n greater or equals to n naught, right? Sorry. Correct? So what happens if you choose epsilon equals to 1 by 2? Correct? So take epsilon equals to 1 by 2. So that means d of x and x should be less than 1 by 2 for all n greater or equals to n naught. This has to happen because xn is converging to x. That is what you are telling me. Correct? So now you see that you have two choices. Either xn is equals to x for all x, and if xn is not equals to x for some n, then d of xn comma x will be 1. Correct? So that means you do not have a choice to xn become not equals to x for any n. Correct? So if xn converges to any x, xn can never be not equals to x, because if there exists some n such that xn not equals to x, then distance between xn and x will be 1. So that means if xn is not equals to x, for some n, then 1 will be less than 1 by 2, which is a contradiction, right? Correct? So this should not happen. Ultimately, if the sequence converges, xn has to be equal to x. Now it matters when it happening. So if let's say it is happening after n0, So that means before like from 1 to n0 doesn't matter what is happening. After n0 all the terms should be equal. Okay, so that means if xn converges to x after a certain natural number n0, all the terms of xn has to be equal to x. Correct? So this implies that if xn converges to x, then there should exist a natural number n0 in n such that xn equals to x for all n greater equals to n naught. Okay,
Yes.
so now tell me what this sequence is now called. So this has a specific name. So do anyone know? So you see that after a certain natural number all the terms are equal, I mean equal to x, correct? And this is called an eventually constant sequence. Okay, so that means if xn converges to x in a discrete metric space, the sequence has to be eventually constant. Okay, so in other words, xn is an eventually constant sequence. Okay, so if you only assume that after certain natural number all the terms in xn are equal, then only xn will converge to that equal number. Now comes to the question. So for the sequence 1 by n, you can see that this is not an eventual constant sequence because all the terms of 1 by n are distinct. Correct? Because n is varying, right? And 1 by n1 is never equals to 1 by n2 for any n1 and n2. Correct? So the sequence is never an eventually constant sequence. So it can never be convergent. So it is a divergent sequence. Is it clear to everyone? Okay. Khushbu is saying got it. What about the others? Have others got it or not? So Nagaraja is said he has understood. What about Binu, Hema, Dibalochan, Dinakaran? Have you guys get it? Okay. Yeah. Finally I got a reply. So then let's go to the next question. Question number 5. Okay. Okay, so let me see what is the next question. Okay, so next question is also an interesting one. So let n be a sequence such that modulus of n converges. So choose the correct option. Okay, so first option is n is convergent. Second option is n is divergent. Third option is n may be convergent or may be divergent. And the fourth option is none of the following above. Okay, so now I'm expecting some answers, so please carefully read the question and then try to answer yourself and then you give an answer to me. So an is a sequence such that modulus of an is convergent. Okay, so then they are asking if modulus is convergent, what about an?
May not be convergent.
Why?
We take the sequence n equal to minus 1 raised to n.
Okay,
The modulo converges to 1. The sequence actually doesn't converge. It oscillates between minus 1 plus 1.
so when it can be true, can you tell me? So I understand that for your example, of course, the question is solved that there are sequences such that modulus of an converges, but an need not be. But I'm asking, is there any, like, what sort of criteria if you put for an such that an will converge provided modulus of an converges? So this is a question for you only, since you have answered correctly, obviously. Yeah, what about others? Okay, so first let me solve the question. So already C has answered that a sequence an is given, so it's an arbitrary sequence, it can be positive, it can be negative. Now if the modulus converges, then a need not be convergent, right? So for example, you take an to be minus 1 to the power n, correct? Then modulus of an is 1, correct, which is convergent, but an is not, right? Correct. So an necessarily not always convergent. Okay, and if you take for example minus 1 to the power n divided by n, then modulus is always 1 by n, that is also convergent, even an is also convergent. So it depends on the sequence. Now my question is what sort of criteria you can put on an such that if modulus of an converges, then an will also converge. So from the answer you can see one thing is that if modulus of an converges to 0, then an will also converge to 0. Is that I mean, does it hold always? So I'm writing as a statement here, so you guys try to tell me or give in an attempt and tell me that if this is true or not. Okay, so if okay, is it true now? Because I have just written as a fact, it need not be true. I mean, it is true, but I mean, why is it true? Anyone? Can you guys give me a proof? Okay, so let's say if an converges to 0, so that means epsilon greater than 0, there exists a natural number such that what? Anyone? Distance between, I mean, this is only true in R, not necessarily in any metric space. So then modulus of an minus 0 will be less than epsilon for each n greater equals to n0, right? And this will imply that modulus of an is less than epsilon for each n greater equals to n0, right? And this is if and only if limit an is 0. Is it clear to everyone? Because other part is always true. If an converges to 0, modulus of an will converge to 0. But if modulus of an converges to 0, then only an will converge to 0. And if the sequence an is positive, then also it is true that if modulus converges, then an will also converge. Okay, but this is a nice case, right? Is it clear to everyone? Because in the last question you see that modulus of an convergent was convergent, but an was not convergent, right? Because of that example, minus 1 to the power n. But for this example, if modulus of an converges to 0, an should converge to 0 and a will always converge to 0 because of the following fact just I have given right now. Correct. So I hope this is clear to everyone, and if not, you can go through it again later, not right now. Okay, so I'll go to the next question. So the sequence n where n is n to the power minus 1 to the power n is a bounded below sequence second option is a convergent sequence third option is a bounded above sequence and yeah, these three options are correct. I mean, these three options are okay. We don't need other options. So, or maybe fourth option you can just give as none of the following above. Okay, so I hope this question is clear to everyone. So the sequence just given by n equals to n to the power minus 1 to the power n. Yeah, anyone? Anyone? Any answer? So I think I had given the definition of bounded above and below, supremum, infimum. This all I have discussed for, I think in the first class probably. I'm not sure, but yeah, I have definitely discussed all of this in the past two or three lectures. So anyone? So what is the sequence actually looks like? So you see that so the sequence will be n to the power minus 1 when n is odd, and n to the power 1 when n is even. Correct? So which is same as 1 by n when n is odd and n when n is even, right? So now, anyone? Tell me.
It is not convergent because
Yes.
n tends to infinity, with 1 is going to 0, 1 is going to infinity, so not convergent.
Okay, what about other options?
If we put 1, then minimum value we are getting is 1. So bounded below.
So that means 1, are you sure? 1 by n is there.
But n we are putting as 1, right? First term.
Okay. So that means you are saying all the terms are greater than 1. So it is bounded
No.
below. What about bounded above? There are three options, right? Bounded below, bounded above, and convergent. Is it bounded above?
The other term is increasing. When it is even, it goes to 4, like that. It increases.
So you said 1 is a lower bound, right?
0 should be the lower bound, no?
Yeah, obviously that's what I'm saying. No, you said 1 or something.
And I was saying 1 should be the term when we first put the n value.
Okay. So the first time you were saying, right?
Yes.
Okay. I know.
But then that decreases 1 by 3, 1 by 5, like that.
Yes. Obviously, then 0 should be on lower bound, right?
Yes.
But yeah. So then, what is the correct option out of 3?
First, bounded below.
Yes. So you see that this is an kind of oscillatory sequence. So for the odd, it is converging to 0. For the even, it is going to infinity. Correct. So a sequence is bounded if and only if all the terms, all the subsequences are bounded. Correct. But you see that even subsequence is not bounded here. Correct. Because it is going to infinity. So that means the sequence, let's say xn. So xn is not bounded. Okay, but 1 by n is converging to 0. So that means 0 is a lower bound for xn. Okay, so xn is bounded below. Okay, now there is no question of asking why it is not convergent, because if a sequence is not bounded, it is never convergent, right? Because convergent sequences are always bounded. So from here we can say that the sequence is only bounded below, correct? Okay, this was an easy question. I hope everyone has got it. So then let's go to the next question. Is it clear to everyone, first of all? Nagraja? Okay, he has put a thumbs up. What about others? Okay. Question number 7. I think this question I have solved in the last class. So consider k equals to union of n equals to 1 to infinity, close 0, close 1 minus 1 by n, then k is compact. Next option is k is closed. Next option is k is bounded. Last option is none of the following above. I think I had solved this question in the last class, probably, as much I remember. So yeah, okay. So yeah, any answer? Anyone? So k is a union of closed intervals, close 0 open, close 0 close 1 minus 1 by n. Then they are asking that if k is compact, close, bounded, or none of the following above. So yeah, anyone? Any suggestions, comments? Like, it can be wrong, that's okay. So you can just like speak, or even you can just put in the chat if you have any opinion. So I had solved this question in the last class, so I'll not repeat the arguments. I had shown that k will be equal to an important set, because it follows from the fact that infinite union of closed set need not be closed. So if you are thinking that set will be closed, it did not be. correct? Infinite intersection of closed sets is always closed, or even any collections of intersection of closed sets are closed, but the union need not be. Okay, so don't always think that it should be a closed set, because infinite union of closed set not is not necessarily closed. So actually this is an exercise to everyone, that K will be close 0 open 1. It is easy to prove. Okay, one side is easy, that uh, close 0, I mean close 0 open 1 is a subset of that set, but you have to prove the other part. Okay, so if you want to know the solution, you can see the previous video where I have already explained, so I am not going to explain it again. Okay, so it was in a other scenario where I have explained this question. So I was explaining other questions such as union of closed sets and intersection of open sets. So there I have written that this union will be closed 0 open 1. Okay, so from here we can see that this set is not closed. Of course it's not compact, because the limit point 1 does not belongs to K, but every element of K is less equals to 1, correct? So K is bounded, right? So K is bounded. Okay, if you want to know the solution, you can see the previous video, I think week 2, and it is available on YouTube. Okay, okay, so let's go to the next question. Question number 8. So let K be a compact subset of R so then which of the following is true? First option is both sub K and inf K exist. Sub K exists but not infimum of K. And then infimum exists but not supremum of K. So this is also an easy question. Okay, so yeah, anyone, any answer? So you guys also can try to do with me. So I think this also I had explained in the first class, I mean the week 1 discussion. Maybe you guys can use it, because by Henneberg theorem complex subsets of R are closed and bounded, right? So anyone, any answer?
From theorem it is both supremum K and infimum K exist.
Yes, this is true, but why? I mean, just you can just explain to me within one sentence.
Eliberal theorem you said before it is a bounded compact. Then how can I explain? I don't know.
Okay, but compact means closed and bounded. I said how I like. I mean, I didn't say that, right? Supremum and infimum exist.
Yeah, but just analyzing myself, but I don't know how can I tell.
Hmm. Okay. So supremum, when it exists, I mean when supremum and infimum of a set exist, I think you guys know, right? If a set is bounded, then only the LUB and GLB exist, right? The least upper bound and greatest lower bound exist, right? So for example, if it is bounded above, then least upper bound exists by the axiom of choice, right? That we have explained. And if it is bounded below, then the infimum exists. Correct. So K is compact implies K is closed plus bounded, right? So now it is bounded implies sup and inf both exist. Correct. Correct. And if K is closed, then both supremum and infimum will belongs to the closed set. Correct. So option 1 is true. Okay, is that clear to everyone? If a set is closed, that means both supremum and infimum will belongs to the set, and boundedness is just only guaranteeing that sup K and inf K exist. Okay, is that clear to everyone? Otherwise I'll go to the next question. This is easy, this is just for information, and if you want to see the proof, you can follow some of the standard books I had referred in the beginning. That you'll see why sup and inf K exist, because you'll go some bunch of theorems and lemmas, I mean axioms of choices, some. Okay. So next question is an important one. So the sequence n where n is square root of n plus 1 minus square root of n is convergent, divergent, it has more than one limit point, and none of the following above. Okay, so this is an important question. Okay, this question probably has been asked before in IIT JAM or maybe in some competitive exams, but this will be helpful to construct a lot of counter examples, especially in sequence and series. Okay, so that I'll be also discussing later. So now, do anyone know what is the answer for this question? Is it convergent, is it divergent, or like does it have more than one limit points? So more than one limit points means it will have at least two subsequences that will converge to two different limits. So then in that case, obviously the sequence will not be convergent if those 2 points are different, right? Because distinct limit points at least two distinct limit points means the sequence is not convergent. A sequence is convergent if and only if all its limit points are equal, right? So yeah, anyone know the answer?
We can rationalize the sequence A by multiplying dividing by root of n plus 1 plus root n.
Okay, then next.
So what we'll get is it is going to be 1 upon root n plus 1 plus root n.
Yeah, so that means
Converges to 0.
converges to 0, right? Yeah. So an always, I mean in this case an converges to 0, correct? So yeah, an is given by square root of n plus 1 minus square root of n, and then you just multiply and divide by square root of n plus 1 plus square root of n, right? So that means it will be n plus 1 minus n divided by square root of n plus 1 plus square root of n, right? Which is same as 1 divided by square root of n plus 1 plus square root of n, correct? Is it clear? This is just conjugation, right? You just multiply by the conjugate on denominator and the numerator. So this implies that limit an is 0. Okay. So that means an is convergent. Is it clear to everyone? Sorry. Okay. So yeah, let me see what other questions are there. Okay, so then let me go to the next question. Which is question number 10. So determine whether x comma y in R2 such that x square plus y square is less equals to 4 and x plus y is greater equals to 1. Is compact. Okay. So is this set compact? First of all, and to prove if the set is compact or not, what to do, like how do we approach? I think in the last class also I had discussed two theorems, if you guys remember. Using that one of the theorems you can prove that the set is compact or not. Oh, Binu is saying circle. What circle? Is it a circle? Are you sure? There are two uh, conditions given, correct? There is not only a circle, there are circle, I mean the inner circle and in the outer region of the line x plus y equals to 1. Are you sure? Is it only a circle? Binu? Okay, yeah, it is not a circle, right? Because if only it was given like x square plus y square less equals to 4, then only you can say this is, even this is not a circle, this is the, like, it's a region, right? This is a set. Circle means x square plus y square equals to 4, or maybe x square plus y square equals to a square, where the center is 0 comma 0 and the radius is a, in case if it is a square. But this is a two conditions are given, that means it will be intersection of two sets. So k can be written as the intersection of two sets. And in fact, you can assume that, or you can see that k can be written as the intersection of two closed sets. So do anyone see that?
Yeah, one set we can take for x square plus y square less equal to 4, one compact set, one closed set, and other for x plus y greater than or equal to 1. Both the sets are closed.
Oh, why you are saying both the sets are closed?
The area which we get x plus y square plus 1 to 4 is rounded, and the border is also included in the set. The entire area is included.
Yeah, I mean that doesn't give an argument, right? Why is it closed? Border is included means a set should be closed. Are you sure? So that means the limit point always lies on the border.
Not necessary.
Okay. Then the sequence 1 by n doesn't have any border, right? I mean, how do you say it has a border or something? So yeah, I mean, you can, I think, I don't know if you guys are following the lectures, I mean the discussions from the last week, but I had discussed one theorems. It says that under continuous function, inverse image of closed sets are closed. Similarly, it is true for open sets. So now K is a subset of R2, right? Which is a finite dimensional Euclidean space. So that means K is compact if and only if K is closed and bounded, right? So you have to just prove that K is closed and bounded, correct? Or if like either of them do not hold, then you can say that K is not compact. So what we're going to do is we're going to prove that in that case the set is compact. Okay. So first we can try to draw the region of both the conditions, and then we can see that it is indeed a compact set, right? So first is a circle, I mean is an inner circle, correct? So this is something like this. Oh. So this is 2 comma 0, okay, because the radius is 2, correct? And another is x plus y equals to 1. So you try to draw the line x plus y equals to 1. So this will be somewhere here, okay? So this line is x plus y equals to 1, correct? So this region will be our K, because you need x plus y greater equals to 1. So this is our K, right? And it includes this whole area. But yeah, it is clear now that the set is bounded, correct? Because it is can be like you can draw a ball of radius, let's say 3, then this region will be always inside that circle of radius 3, right? So you can just take a big circle, something like this, then the region always inside the circle, and not only that, even this region is always inside that own circle, that x square plus y square is equals to 4, right? So clearly the set is bounded, there is no doubt. But what about closeness, right? That is what you have to prove. So as I have explained in the last class, please see the video, that or also try to prove that under continuous function, inverse image of closed and open sets are open and closed. Okay, so now what you're going to do is we're going to define two functions and try to prove that K is a closed set. Okay, so from here we can see that K is bounded, correct? Because you can say that for each x and y in K, this norm of x comma y is less equals to 2. Okay, so here the norm is the Euclidean norm. So this is a 2 norm. So 2 norm is defined like this. Okay, so to prove the closeness, we define two functions. One is this one and another is this one. Okay, so both f and g are function from R to R, let's say. Okay, so one thing you can notice is that both f and g are continuous function, because they are both polynomial function, and polynomial functions are always continuous, right? So in multivariable calculus, you might have seen that this function is continuous and gxy is also continuous. Okay, I don't know if you guys have taken the course multivariable calculus. Probably you will see. I think in graduation this is taught also. In masters, so definitely multivariable calculus should be taught. So in particular, you can say G is a linear function in two variables x and y, and f is a quadratic function, right? So both f and g are continuous. Sorry, it's not from R to R, it should be from R2 to R, because there are two arguments, right? It should not be only R, because you are putting two variables x and y, right? So now you can see that this set f inverse of four comma infinity intersection g inverse of sorry, this should be 0, 4, I think, yeah. Wait, so f inverse of minus infinity comma 4 intersection g inverse of 1 comma infinity is our given K. Okay, because let's say x comma y belongs to K, then x comma y will belongs to both f inverse of minus infinity comma 4 and x comma y belongs to g inverse of close interval 1 comma infinity. Okay, so here inverse is not the function inverse, it is just the pre-image. So in that sense this is the inverse. Okay, this is not the function inverse, this is the inverse of, like for example, if f of a equals to 2, then f inverse 2 is a, right? So from here, let's say if x comma y belongs to k, then x comma y belongs to both of these two sets, right? F inverse of minus infinity comma 4 and g inverse of 1 comma infinity. Now you see that f inverse of this set is x comma y in R2 such that x square plus y square is less equals to 4, and this set is x comma y in R2 such that x plus y is greater equals to 1. Okay, and as I said that inverse image of closed sets are closed under continuity, and because both these two sets are closed, minus infinity comma 4 and 1 comma infinity, both are closed sets. Correct. So intersection of two closed sets are closed, so that means K is closed. Is this clear to everyone how I did it?
Yes.
What about others? So yeah, let me write it here. Since minus infinity comma 4 and 1 comma infinity are closed sets, therefore f inverse of minus infinity comma 4 and g inverse of 1 comma infinity both are closed. Okay, hence K is closed. So K is closed and bounded. Implies K is compact, because already we have proved that K is bounded. We have now just proved that K is closed. By Henry-Borel theorem, K should be compact because K is a subset of R2. Okay, so I hope this is clear to everyone. This is, I mean, using this theorem you will be able to solve a lot of questions in the upcoming competitive exams, okay, such as NET and GATE also. This is a really important theorem. Always remember. Also I had given one exercise that inverse image of bounded sets need not be bounded. Okay, I'm telling it again. Inverse image of bounded sets are not bounded. So that means inverse image of compact set need not be compact, but inverse image of closed set will be closed under continuity. Okay, under continuity, inverse image of closed sets and open sets will be closed and open respectively, but it did not hold for bounded and compactness. Okay. However, under continuity, compactness is preserved. So that means inverse image of compact set is not compact, but the image is always compact. Not only image, I mean, not only compactness, you can prove that connectedness, compactness, all are preserved under continuity. Okay, if a set is compact and connected, and if the function is continuous, their image should be compact and connected respectively. So I hope this is clear to everyone. So if you have any doubts, you can ask me. Otherwise, we'll solve the last question, which is question number 11. Okay, so can anyone answer to me? Why this set is not compact? Is this set closed? Like I want to know like how you guys have learned now, since I have given the theorem that inverse image of closed and open sets are closed and open. So what you have to do is you have to just find out the function and what kind of inverse you have to take. Like you have to see that what kind of inverse image of closed set you have to take such that the inverse will be closed. The inverse image will be closed. Anyone? Dipasri, Nagaraja, Kushbu, Dinakaran, Dibalochan and Binu. Okay, so first see that you have to construct a function such that the inverse image would be exactly h under continuity, obviously. So we already know that h is a hyperbola, correct? So you already probably know that this looks like this, correct? So this is xy equals to 1. So clearly the set is not bounded, it's going to infinity as like y going to 0 or x going to 0, y is going to infinity because y equals to 1 by x, correct? Yeah, h is not bounded definitely because you see y equals to 1 by x. As x goes to 0, this will go to infinity, correct? So not only that, at x goes to, like if limit x tends to 0 positive, 1 by x will be positive infinity, and similarly it will go to negative infinity if it approaches from left side, and limit x tends to 0 negative, 1 by x is negative infinity. Okay, so clearly the set is not bounded. What about compactness? Is it compact? Yes, 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 it is not bounded definitely. Yeah, not compact. Yeah, Dinakaran, I have understood. Yeah, you're correct. This is not a compact set, but I'm asking, is this closed? Is H closed? Why it is closed? Dinakaran, can you tell me? Yeah, just one line hints can you give me, such that I can understand. Yeah, you know that H is closed. I mean, yeah, of course we can write that H equation. I mean, asking that how do you write, I mean, what is the function, what is the continuous function? Yes, yes, what is the continuous function you are taking here, and what is the pre-image, like which closed set are you taking as the pre-image such that the inverse image is the whole of H? Okay, so let me write it here. So you take this function, okay, so this is a continuous function. Yeah, f inverse of 1, correct. So then f inverse of 1 is whole of H, correct, and singleton of 1 is a closed set in R. So this, by continuity, f is also, I mean, f inverse of 1 is also closed, so that means H is closed. So H is closed, right? So the boundedness do not follow, because you can see that this sequence belongs to H for all n, correct? But you see that this 2 norm of this number looks like this, okay, and you can prove that this is greater or equals to square root of 2, okay, so that means it belongs to square root of 2 comma infinity, okay. So in other words, or we should say like this, because as n grows, 1 by n square will go to 0, but n square will go to infinity, okay, so the sequence will diverge to infinity. So that means we are getting sequence, I mean, we're getting elements from H that are arbitrarily large, correct? So that means H cannot be bounded, so H is not compact, okay. So I have given 2 arguments for boundedness, one using the function, another using the sequence, and both are almost same, okay. The sequence arguments follows from the definition of the function I had given like this, because we are choosing y equals to 1 by x. So if you choose x to be n, y will be 1 by n, and there is a criteria for sequence in continuity. I don't know if you guys know it, so you guys can see all of this definition in the chapter continuity, okay. But for now I encourage to everyone, so please read and try to solve some questions from sequence, continuity, compactness, and then other topics that has been taught in this week. So then you guys like will have more graphs on the topics, okay. So is this question clear to everyone? Otherwise we're gonna stop today. So please put a thumbs up if you have understood this question, and if you don't, then you can just tell me, I'll explain it again, okay. Yeah, I hope everyone has understood, right? This is simple, right? Just an application of the main theorem, isn't it? Okay guys, see you, bye, and good night.